Welcome to this walkthrough of LeetCode problem number 335, self-crossing. In this problem, we'll explore a fascinating challenge that involves determining whether a path defined on a 2D plane crosses itself. This is a great opportunity to practice working with geometric logic and edge case analysis. Let's dive in. In this problem, you are given an array of integers called distance, which represents the sequence of movements for a robot on a 2D plane. The robot starts at the origin, which is the point 0, 0, and moves according to specific rules. First, it moves upward by the value of distance, 0. After that, it moves left by the value of distance, 1, then downward by distance, 2, and finally right by distance, 3. Once these 4 steps are completed, the robot continues to move in the same sequence up, left, down, and right for the remaining values in the distance array. The goal is to determine whether the robot's path crosses itself at any point during its journey. If it does, you should return true, otherwise, return false. The input to this problem is an array of integers, distance, which defines the number of steps the robot takes in each direction, in order. The length of this array, denoted as distance.length, determines how many steps the robot will take overall. Each element in the array, distance, I, represents the distance the robot moves in the respective direction, and it satisfies the condition that I is between 0 and distance.length 1. The output is a Boolean value, true if the robot's path crosses itself at any point, and false if it does not. Let's look at some examples to understand this better. In the first example, the input array is distance equals 2, 1, 1, 2. The robot starts at the origin and moves up by 2 units to reach the point 0, 2. Next, it moves left by 1 unit to -1, 2. It then moves downward by 1 unit to -1, 1, and finally, it moves right by 2 units to 1, 1. At this point, the robot's path crosses itself at the point 0, 1, which was part of its previous path. Therefore, the output for this example is true. In the second example, the input array is distance equals 1, 2, 3, 4. The robot starts at the origin and moves up by 1 unit to the point 0, 1. Then, it moves left by 2 units to -2, 1. After that, it moves downward by 3 units to -2, -2. Finally, it moves right by 4 units to 2, -2. Throughout this sequence, the robot's path does not intersect with itself, so the output for this example is false. In the third example, the input array is distance equals 1, 1, 1, 1. The robot starts at the origin and moves up by 1 unit to 0, 1. Next, it moves left by 1 unit to -1, 1. Then, it moves down by 1 unit to -1, 0, and finally, it moves right by 1 unit to return to the starting point, 0, 0. Since the robot's path returns to its initial position, it crosses itself, making the output for this example true. There are some important constraints and edge cases to consider for this problem. First, the length of the distance array, distance.length, can range from 1 to 10,000, and each value in the array, distance, I, can range from 0 to 10,000. For edge cases, if distance.length is less than 4, the robot cannot complete a full cycle of movements, so the path cannot cross itself, and the output will always be false. Additionally, if all values in distance are 0, the robot does not move and trivially crosses itself at the origin point. For larger arrays or values, the algorithm must be efficient to handle up to 10,000 steps without timing out. Lastly, there are scenarios like non-crossing spirals or immediate crossings within the first few steps that require careful handling to ensure correctness. To solve problem number 335, self-crossing, we need to determine if a path in a 2D plane formed by a sequence of movements intersects itself. The path is defined by an array of distances, with the robot alternating directions in the order of up, left, down, and right. A straightforward way to approach this is through a brute force simulation. Here, the idea is to simulate the robot's movement step by step, keeping track of every line segment it creates. For each new segment, we check if it intersects with any of the previous segments. This is done by storing the coordinates of all visited segments and performing geometric checks for intersections. While this approach is intuitive and easy to implement, it has a time complexity of n², since each new segment must be compared against all prior ones. Additionally, its space complexity is O(n), as we need to store all visited segments. Although simple, this method becomes computationally expensive with larger input sizes, leading to the need for a more efficient solution. A more efficient way to handle this problem is by using geometric rules to detect self-crossing. Instead of storing all the visited segments, we focus on analyzing the relative lengths of the most recent segments to identify crossing patterns. Through careful observation, we can classify self-crossing into three distinct cases. First, the fourth segment can cross the first; second, the fifth segment can meet the first; and third, the sixth segment can intersect the first. By tracking just the last 4 to 6 segments, we can identify these cases efficiently. The process involves iterating through the array of distances and performing simple comparisons to check for these geometric conditions. This approach is highly efficient, with a time complexity of O(n), as each segment is processed in constant time, and a space complexity of O(1), as we only need to maintain a small set of recent segments. Although this method requires careful attention to detail when implementing the geometric conditions, it is both elegant and computationally optimal for this problem. Another potential solution is the sweep line algorithm, which dynamically detects intersections using a balanced data structure. In this technique, we maintain a set of active line segments and perform updates as new segments are added. This method requires sorting and dynamically managing the segments, which results in a time complexity of O(n) log n. The space complexity is O(n) due to the need to store active segments. While this approach is powerful and widely applicable in computational geometry, it is unnecessarily complex for this specific problem. Since the geometric rules in the previous approach already provide an efficient solution in linear time and constant space, the additional overhead of the sweepline technique is not justified here. The optimized approach based on geometric rules is the clear choice for this problem. By focusing on the relative lengths of the last few segments, we can detect self-crossing locally without the need to compare every segment globally. The key insight is that self-crossing can only occur under specific conditions within the most recent movements, allowing us to limit the scope of our checks. This results in a solution that is linear in time and constant in space, making it highly efficient for large inputs. The brute force method, while easy to understand, is far too slow for larger datasets due to its quadratic time complexity. Similarly, the sweepline algorithm introduces unnecessary complexity for a problem that can be solved using simpler geometric analysis. By leveraging these observations, the chosen strategy provides an elegant balance of simplicity, efficiency, and correctness, making it the ideal solution for self-crossing. In this problem, we are tasked with determining whether a robot's movement in a 2D plane crosses itself. The movements are defined by an array called distance, where each element specifies how far the robot moves in one of 4 cyclic directions: up, left, down, and right. Starting at the origin, each movement forms a line segment, and the goal is to check if any of these segments intersect. To solve this, we first need to understand the movement cycle. The robot repeats the directional pattern of moving up, left, down, and right sequentially, with each movement defined by the distance array. The challenge arises when these segments overlap, which can happen in 2 main ways. First, the current segment might intersect the previous segment, such as when the robot doubles back. Second, a segment might intersect with an earlier one further back in the sequence, forming a loop. To detect these scenarios, we'll iterate through the distance array, calculate the coordinates of each segment, and check for intersections as we go. Now, let's explore how to check for intersections. There are 3 main geometric cases to consider. First, the simplest case occurs when the current segment intersects the segment 2 steps back. This happens when the robot's path doubles back immediately. Second, the path might intersect a segment 3 steps back. This typically happens when the robot moves in a way that creates a square or rectangular loop. Finally, there's a more complex case where the path spirals inward and crosses a segment that's even farther back in the sequence. To handle these cases efficiently, we need specific rules for detecting intersections. For instance, if we're at the 4th segment or later, we can check whether the current segment overlaps with the one 2 steps back using a simple inequality. For 5 or more segments, additional conditions are required to account for overlaps with segments further back, including the inward spiral scenario. Importantly, this algorithm only checks the relevant nearby segments for each new movement, which keeps the time complexity at O(n). This efficiency is achieved by recognizing geometric patterns and avoiding unnecessary checks. However, we must also account for edge cases, such as when the input array is very small or when the distances are extremely large, which could create unique challenges. To implement the solution, we rely on the distance array directly to represent the robot's movements. We calculate the robot's position and use these calculations to implicitly track the segments formed. Let's examine the core implementation. First, if the array has fewer than 4 elements, we can immediately return false, as it's impossible for the path to cross itself with fewer than 4 movements. Next, we iterate through the array starting from the 4th movement. For each movement, we check the 3 cases of intersection using precise conditions. In the first case, the current segment crosses the segment 3 steps back. This is checked using a simple inequality involving the current and prior distances. For the second case, where the current segment crosses the segment 4 steps back, additional checks are required to confirm overlap. Finally, the third case handles the inward spiral, where the current segment crosses the segment 5 steps back. Here, the conditions are more complex, involving multiple inequalities that compare the distances of overlapping segments. If any of these conditions are satisfied during the iteration, the function returns true, indicating an intersection. If none of the intersection conditions are met throughout the iteration, the function concludes by returning false, indicating no self-crossing. Now, let's analyze the complexity of this solution. The time complexity is O(n), where n is the length of the distance array. This is because each segment is checked against a constant number of previous segments, regardless of the array size. The space complexity is O(1), as the algorithm does not require additional data structures beyond a few variables for calculations. This makes it highly efficient in terms of memory usage. It's also designed to handle edge cases effectively. For example, if the input array is too small, the function exits early. Large values in the distance array are not an issue, as Python handles arbitrarily large integers natively. Additionally, if the robot's movements form a straight line without turning, the algorithm will correctly return false, as there are no overlapping segments. By combining efficient geometric checks with robust handling of edge cases, this solution ensures accuracy and optimal performance for all valid inputs. This implementation solves the LeetCode problem self-crossing by systematically checking for 3 specific cases of self-crossing patterns based on geometric rules derived from the movement directions. Each movement corresponds to a line segment, and the task is to detect if any segment intersects with a previous one. The function first checks if the number of movements is less than 4, as self-crossing is impossible in such cases. Then, it iterates through the distance array starting from the 4th step, index 3, because crossing only becomes possible at that point. For each step, the algorithm evaluates 3 cases. 1. Case 1, the current line intersects the line 3 steps ahead. This happens when the current step's distance is greater than or equal to the distance 2 steps back, and the previous step's distance is less than or equal to the distance 3 steps back. 2. Case 2, the current line intersects the line 4 steps ahead. This occurs when the previous step's distance equals the distance 3 steps back, and the sum of the current step's distance and the distance 4 steps back is greater than or equal to the distance 2 steps back. 3. Case 3, the current line intersects the line 5 steps ahead. This is the most complex case and requires multiple conditions to hold simultaneously, involving comparisons across 5 previous steps. If any of these conditions are met during the iteration, the function immediately returns true, indicating a self-crossing. If the loop completes without finding any intersections, the function returns false. This approach is efficient with a time complexity of O(n), as it processes each step in the distance array once. The space complexity is O(1), since it uses only a constant amount of extra space. Here, we begin by defining a class called solution and implementing the method isSelfCrossing, which takes an array of integers called distance as input. This array represents the lengths of consecutive movements in a path. The goal is to determine if this path crosses itself at any point. First, we check if the array has fewer than 4 elements. If it does, the path cannot possibly cross itself, so we return false. Next, we use a for loop starting from index 3 to iterate through the distance array. This is because self-crossing can only start to occur after at least 3 steps. Within the loop, we handle three distinct cases of self-crossing. In the first case, we check if the current line crosses the line 3 steps ahead of it. This happens if the current distance is greater than or equal to the distance 2 steps ago, and the previous step is less than or equal to the distance 3 steps ago. If this condition is true, we return true, indicating that the path crosses itself. Moving on, we handle the second case, where the current line crosses the line 4 steps ahead. This occurs when the previous step equals the distance 3 steps ago, and the sum of the current distance and the distance 4 steps ago is greater than or equal to the distance 2 steps ago. If these conditions are satisfied, we again return true. Finally, we address the third case, where the current line crosses the line 5 steps ahead. This involves several conditions. The distance 2 steps ago must be greater than or equal to the distance 4 steps ago. The sum of the current distance and the distance 4 steps ago must be greater than or equal to the distance 2 steps ago, and the previous step must be less than or equal to the distance 3 steps ago but also large enough that the sum of the previous step and the distance 5 steps ago is greater than or equal to the distance 3 steps ago. If all these conditions are met, the method returns true, signifying a self-crossing path. If none of the conditions for self-crossing are met during the loop, the method completes its iteration and reaches the return statement at the end. Here, we return false, indicating that the path does not cross itself. This ensures that the method handles all possible scenarios and provides the correct result. With this implementation, we can efficiently check for self-crossing in a path using a single traversal of the array, making it both time and space efficient. In this example, we are given the input distance array, 2, 1, 1, 2. This array describes the distances of consecutive movements in the order of north, west, south, and east. The length of the array is 4, so we enter the loop starting from index I equals 3. At this iteration, we evaluate case 1. Here, distance I is 2, distance I2 is 1, distance I1 is 1, and distance I3 is 2. The condition for case 1 requires that distance I is greater than or equal to distance I2, which is true as 2 is greater than or equal to 1, and that distance I1 is less than or equal to distance I3, which is also true as 1 is less than or equal to 2. Since both parts of the condition are satisfied, the function concludes that the path is self-crossing and immediately returns true as the output. Here, we examine the input distance array 1, 2, 3, 4. Again, the distances represent movements in the order of north, west, south, and east. The length of the array is 4, so we start the loop at index I equals 3. In this iteration, we first evaluate case 1. For case 1, distance I is 4, distance I2 is 2, distance I1 is 3, and distance I3 is 1. The condition requires that distance I is greater than or equal to distance I2, which is true as 4 is greater than or equal to 2. However, the second part of the condition, which checks if distance I1 is less than or equal to distance I3, is false because 3 is not less than or equal to 1. Since case 1 is not satisfied, we move to check case 2, but this case does not apply because I is less than 4. Similarly, case 3 is not applicable as I is less than 5. With no conditions satisfied, the loop ends, and the function concludes that the path is not self-crossing, returning false as the output. Now, we analyze a more complex input, 2, 1, 4, 3, 2. The length of this array is 5, so we start the loop at index I equals 3. In this iteration, we evaluate case 1. Here, distance I is 3, distance I2 is 1, distance I1 is 4, and distance I3 is 2. The condition for case 1 requires distance I to be greater than or equal to distance I2, which is true as 3 is greater than or equal to 1. However, the second part of the condition, which checks if distance I1 is less than or equal to distance I3, is false because 4 is not less than or equal to 2. Since case 1 is not satisfied, we proceed to the next iteration, where I is now 4. At this stage, we check for case 2. Here, distance I is 2, distance I2 is 4, distance I1 is 3, distance I3 is 1, and distance I4 is 2. The condition for case 2 requires distance I1 to be equal to distance I3, but this is false as 3 is not equal to 1. Therefore, case 2 is also not satisfied. Finally, we check for case 3 in the same iteration where I is 4. For case 3, distance I is 2, distance I2 is 4, distance I1 is 3, distance I3 is 1, and distance I4 is 2. The condition for case 3 involves 3 parts. First, distance I2 must be greater than or equal to distance I4, which is true as 4 is greater than or equal to 2. Second, distance I plus distance 1, 4 must be greater than or equal to distance I2, which is also true because 2 plus 2 equals 4, meeting the condition. However, the third part of the condition, which requires distance I1 to be less than or equal to distance I3, is false since 3 is not less than or equal to 1. As a result, case 3 is not satisfied. With no conditions met during the loop, the function concludes that the path is not self-crossing and returns false as the output. Here, we analyze the time complexity of the solution. The provided algorithm operates with a time complexity of O(n), where n is the number of elements in the input list distance. To understand this, let's first consider that the input list has n elements, each representing the length of a step in the path. The algorithm starts iterating from the fourth element, which corresponds to index 3, and continues to the end. This means the loop executes at most n 3 times, which simplifies to O(n). Inside this loop, the algorithm evaluates 3 conditions to check for intersections. These checks involve simple arithmetic comparisons, such as verifying if the current step overlaps with a previous one. Each of these operations is constant time, or O(1). When we multiply the O(n) iterations of the loop by the O(1) operations performed in each iteration, the overall time complexity remains O(n), making the solution efficient for large inputs. Now, let's consider the best, average, and worst cases. In the best case scenario, the algorithm detects a self-crossing early on and exits the loop. The time required in this case is OK, where k is the index of the first intersection, and k is less than n. For the average case, the loop processes most of the elements before finding a crossing. However, this still scales linearly with the size of the input, resulting in an O(n) complexity. Finally, in the worst-case scenario, no self-crossing is detected, and the loop runs through all n elements, also resulting in O(n). Shifting to space complexity, the solution uses only a constant amount of extra memory, or O(1). This is because there are no additional data structures allocated, and the algorithm operates directly on the input list. To understand why the space complexity is O(1), let's break this down further. The memory usage of the solution is minimal and remains constant regardless of the input size. For instance, the variables like n, which stores the length of the input, and the loop index I, are scalar values that require constant space. Within the loop, the algorithm only refers to specific values from the input list, such as distance I or distance I2. This means no new data structures are created, and the input list itself is neither modified nor duplicated. Since the algorithm simply reads values from the input without allocating any additional memory that scales with n, the space complexity is O(1). This makes the solution highly space efficient, as it only uses a fixed amount of memory, regardless of how large the input list becomes. Let's compare this solution with a brute force or naive approach to highlight its efficiency. A naive method might involve tracking the entire path by storing the coordinates of each step and then checking for intersections explicitly. This would result in a time complexity of O(n squared, as each new step would need to be compared against all previous steps to detect overlaps. The space complexity in this case would also be O(n), since storing the coordinates of all steps would require memory proportional to the input size. In contrast, the provided solution avoids these inefficiencies by leveraging geometric properties to detect intersections directly, reducing the time complexity to O(n), and the space complexity to O(1). Mathematically, the solution achieves O(n) time because the loop runs n 3 times, and each iteration involves constant time operations. Similarly, the space complexity is O(1), as no additional memory is used. This optimization makes the solution significantly better in terms of both time and space compared to the naive approach. One of the most common mistakes in solving the self-crossing problem is not accounting for all the possible crossing patterns. There are 3 distinct scenarios you need to handle: the path spiraling inward, overlapping adjacent edges, and intersecting non-adjacent edges. If any one of these is overlooked, your solution could fail in edge cases. It's crucial to test your implementation with examples that cover all these patterns to ensure correctness. Another frequent error is assuming the path always moves inward or outward in a spiral-like fashion. That's not always true. Paths can alternate between expanding and contracting, so your logic must accommodate this variability. Additionally, it's easy to overlook boundary checks when accessing the distance array. For example, when referencing distance I4, you need to confirm that I is at least 4 to avoid index out-of-bounds errors. Another pitfall is relying on a brute force approach that checks all previous segments for intersections. While straightforward, this method has a time complexity of n squared and becomes inefficient for larger inputs. Optimizing your solution to n by leveraging geometric conditions is critical for performance. Lastly, edge case testing is often neglected. Scenarios like very small arrays, large arrays without crossings, or paths that barely cross are all essential to validate your solution against subtle bugs. This problem is a great exercise in understanding geometric relationships between segments, which is a key pattern to keep in mind. A helpful strategy is to visualize how the path evolves step by step, as this can clarify the conditions under which crossings occur. During an interview, it's important to prioritize optimization. While a brute force solution may serve as a starting point, interviewers will expect you to refine it to n for large inputs. Make sure to clearly explain your logic, particularly the 3 crossing conditions: spiral inward, overlapping adjacent edges, and non-adjacent intersections. Diagrams or specific examples can be very effective in illustrating your thought process. Edge cases are another area interviewers often explore to test the robustness of your solution. Being proactive about discussing these cases demonstrates thoroughness and a strong understanding of the problem. Additionally, this problem is connected to other computational geometry challenges. For example, LeetCode 149, max points on a line, involves understanding geometric relationships, while LeetCode 587, erect the fence, requires handling edge cases in computational geometry. Even problems like LeetCode 202, happy number, which involves cycle detection, can offer conceptual parallels to the self-crossing problem. Exploring these related problems can help you build the skills necessary to approach this challenge effectively. One of the optimal approaches to solving the self-crossing problem is to use geometric condition checks. This method evaluates whether a new segment crosses any of the previous ones in constant time per segment, bringing the overall complexity down to n. However, implementing this approach requires careful attention to detail, as the logic can be tricky to debug. Another approach is the brute force method, where you compare every new segment with all previous segments for intersections. While this is the simplest to implement, it has a time complexity of n squared, making it unsuitable for larger inputs due to inefficiency. A third alternative is simulating the path on a 2D grid. By tracking all visited points, you can detect crossings based on whether a point is revisited. This approach, however, comes with a trade-off: it uses more memory, approximately n, and may still be slower than the optimal geometric checks. Each of these methods has its pros and cons, so the choice depends on the specific constraints and the level of optimization required. Great job! We've successfully covered LeetCode problem number 335, self-crossing. To summarize, we tackled a geometric problem with edge case analysis, achieving an efficient solution. Remember to practice problems like this to strengthen your understanding of geometric logic. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!